This little video I'm going to look at how to represent a number using floating point. I'm going to pick a nice easy number for myself, 3.5 and Denary, which is obviously base 10. Now it's base 10 because there's 10 digits. Those digits in base 10 are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. 10 different digits that we use as human beings to create numerical values, but computers are obviously base, if I could write that'd be lovely, base 2. Base 2 obviously only has 2 digits, binary, 0 and 1. So if I want to represent 3.5 from denary to binary, well that's going to be very straightforward. I'm going to make my grid first of all of in fact, I'm going to go first of all to a thing called fixed point. I'm going to travel the floating point binary, but I'm going to start off at fixed point binary. Fixed point binary has a binary place and 3 values on the right and 5 values on the left. The 3 values on the right are a half, a quarter, and an eighth. Progressively smaller. The 3 values on the left are the usual values you would find in binary. They are 1, 2, 4, 8, I'm just squeezing it in a little bit, and 16. Now, fixed point notation also uses a thing called 2's complement, which means that the most significant bit is a negative value. So that is not 16, that is actually minus 16, not 16. So I don't need to worry about the 2's complement particularly. I've given myself a nice easy task. Converting 3.5 using fixed point notation is straightforward. I'll have a 2, I'll have a 1. I don't need any of these other values. And what else do I need? A 0.5 is the same as a half, so that's just a 1 for a half, nothing for a quarter, and nothing for an eighth. So 3.5 and fixed point base 2, fixed point binary can be represented like that. But I want to take the next step and I want to convert that to floating point, and I want to convert it to fully normalized floating point. Now, this is a positive value. The rule for normalized positive values is that it should always start with 0, 1. If it was a negative value, then it would have to start with 1, 0. So for this to start with 0, 1, I will have to move that binary place once, twice. So the binary place will have to be moved to there. Now I can do that, and straightforwardly enough. So I'm going to have a series of binary values here. I'm going to stick with the original 3 zeros. Not that that matters. I'm going to put on my binary place 1, 1, 1. So at this point, it could be said that I have a 6-bit mantissa. My number is represented by 6 bits currently. If I was to just strike those 2 off, because zeros don't have any value in this context, if I was going to strike those off, then I could get away with having a 4-bit mantissa instead. So this is my 4-bit mantissa, which is my actual numerical value. Next, I need to represent that I've moved my binary place twice. So to get back to the original number, I will need to move my binary place twice to the right. So I will need an exponent for that. My exponent will have to contain the binary value for 2, positive 2, because to get back to the original value, I need to move that once, twice to the right. If I move that twice to the right, I would have 1.1, which would be 2 plus 1 is 3 and a half. Straightforward enough. So to represent a positive exponent with the value plus 2, I'm going to say that I'm going to use a 4-bit exponent as well. All of this is also done with 2's complement. So my 4-bit exponent would have 4 possible values, 1, 2, 4, and minus 8 because of 2's complement. I want to represent the value positive 2. I don't need a minus 8. I don't need a positive 4. I do need a positive 2. That leaves no remainder. So actually, I've gone from 3.5 in base 10 binary to fully normalized version of that and floating point 3.5 positive binary, positive denary, to fully normalized as 0.111 for the mantissa and 0.010 for the exponent. I would need to clearly state that I have a 4-bit mantissa and a 4-bit exponent.